previous video covered the main body of information regarding types of solids. I want to discuss atomic solids in more detail in this video. The majority of atomic solids would be metallic solids, metal cations in a uniform lattice surrounded by free-floating valence electrons. The noble gases also exist as atomic solids, non-bonding atomic solids. Just as a reminder, we learned way back in Chem 1 that these 7 nonmetals always exist as diatomics in nature, so they're considered molecular solids, not atomic solids. A handful of elements can exist in multiple forms called allotropes. I put the term allotropic in parentheses to emphasize the point that this is not a type of solid. It's a word that means the element exists in multiple forms in nature. For example, while oxygen commonly exists as the diatomic molecule O2, it has a second elemental form, ozone, O3. O2 and O3 are allotropes of oxygen. I'll talk about allotropes of carbon later in this video. I'll also talk later about several network solids that exist. Metallic solids come in 2 types: pure substances like elemental copper and alloys like brass or bronze or steel. Alloys always contain at least one metal. Most metallic materials that we come in contact with on a daily basis are actually alloys. A pure metal is combined with other substances to improve its properties, to make it stronger or harder or lighter. Take iron, for example. It's very strong, but it can be quite brittle and it rusts easily in damp air. Aluminum is very light, but in its pure form it's too soft and weak to be used as a building material. Let's go back to iron. It's a great building material, but alloy it with carbon to make steel, and the resulting alloy is stronger and harder and, most importantly, rust-proof. Aluminum is very light but also very soft. Add small amounts of the metals magnesium, manganese, and copper, and you get an alloy which is used in making airplane bodies. Alloys always show improvements over the main metal in one or more of their physical properties. Alloys form in 2 different ways. Substitutional alloys form between atoms of comparable radii, like copper and zinc. Atoms of one element are removed from the lattice and replaced by atoms of the other element. Interstitial alloys, on the other hand, form between atoms of very different radii. The smaller atoms fill in the small spaces between the larger atoms. In steel, small carbon atoms exist in the spaces between the iron atoms. No iron atoms are removed. Small carbon atoms are added into existing spaces. Remember from the previous video, network covalent solids have atoms at the points of the lattice, which is why this is a type of atomic solid. But this type is different from the other atomic solids because these atoms are held together by true covalent bonds. There aren't many examples of this. Only certain nonmetals form network solids. Several allotropes of carbon, elemental silicon, silicates, which are compounds that are an array of silicons and oxygens, as well as the compound silicon carbide. One example of a silicate, silicon dioxide, is a molecular compound with the empirical formula SiO2. It's a 3D array of silicons and oxygens, all covalently bound together. Each silicon is surrounded by 4 oxygen atoms. Several allotropes of elemental carbon are network solids. One form of carbon, coal, is an amorphous solid. It has no regular internal pattern. Diamond, graphite, and fullerenes are all network solid allotropes of carbon. Let's talk about each of these network covalent allotropes. In diamond, each carbon is sp3 hybridized, meaning that each carbon is covalently bound to 4 other carbons. As a result of this 3D array of strong sigma bonds, diamonds are very hard, have very high melting points, and are a non-conducting solid. Another allotrope of carbon, graphite, is different. Graphite consists of sheets of carbons that are covalently bound to each other, but each sheet is not bound together. Graphite consists of layers of sp2 hybridized carbons. Remember that sp2 hybridization results in 120-degree bond angles and an unhybridized p orbital perpendicular to the hybrid set. In graphite, this creates flat sheets of 6 carbon rings. The unhybridized p orbitals extend above and below each sheet, resulting in a huge delocalized pi bond cloud above and below each sheet. Electrons can move around throughout these delocalized orbitals, which means layers of graphite can slide across one another. This is how you write with a graphite pencil. You press the tip to paper. As you move the pencil, layers of graphite slide off the tip of the pencil and adhere to the paper. There's a third allotrope of carbon that is also a network solid, a family of molecules called fullerenes. The first and maybe most famous fullerene is Buckminster fullerene, a sphere of 60 carbon atoms in the same conformation as a soccer ball. Fullerenes can be spherical, elliptical, or a hollow tube of carbons bound into rings. An example of this, carbon nanotubes, are being actively studied by many research groups. Let's move on and talk a little about silicon. Silicon atoms form a 3D network similar in geometry to diamond. Silicon, as a metalloid, is a semiconductor, a material intermediate between a true conductor, like most metals, and an insulator, like most nonmetals. The conductivity of silicon increases as temperature increases. The conductivity of silicon can also be increased through a process known as doping. Time out on that term while we discuss band theory and how it applies to conductivity. Band theory arises from the idea in molecular orbital theory that orbitals are delocalized throughout an entire material. Band theory says that all the occupied molecular orbitals, those orbitals that contain the electrons in the ground state, occupied molecular orbitals in an entire crystal are thought of as one group called the valence band. Then there's the other molecular orbitals that can exist but are not used when the sample is in the ground state. Those as a group are called the conduction band. Band theory says that a material can conduct electricity when electrons are able to transition from the occupied molecular orbitals, the valence band, into the previously unoccupied higher energy molecular orbitals of the conduction band. Materials are conductors by nature if their valence band and conduction band are continuous. There's no energy gap between them, so electrons can readily make the transition up into the conduction band. Materials are insulators when there's a large energy gap between the valence and conduction bands. Understand that when I use the phrase electrons become mobile, that's a way of saying the material can conduct electricity. Semiconductors, then, are materials with a small but a significant band gap between the valence and conduction bands. Electrons are able to make the jump, but not all the time, not in all circumstances. Semiconductors conduct electricity in some conditions, like increased temperatures, but not at all conditions. One way to make semiconductors more effective is by adding small amounts of impurities that in one way or another allow for greater electron movement. This is referred to as doping. Let's look at two different versions of doping silicon to increase its conductivity. One option is to add a group 5A element like phosphorus to the silicon crystal. Phosphorus has 5 valence electrons compared to 4 in silicon. That additional electron from each added phosphorus is placed into a conduction band. It doesn't have to gain energy to get promoted into the conduction band. The extra electrons have no space in the valence band. They automatically enter into the conduction band. The resulting material is called an N-type semiconductor because the additional negative electrons from the doping material is what increases the conduction. Another option to increase silicon's conductivity is to add a group 3A element, like gallium, to the crystal. Group 3A elements have only 3 valence electrons, one less than silicon. This results in empty spots in the valence band, spots that aren't filled by electrons. The electrons that are in the valence band can move from hole to hole. This material would be referred to as a p-type semiconductor. The holes in the valence band are thought of as positive voids that the electrons can move into. So there you are. More information than I'm sure you've ever wanted to know about types of atomic solids.